Alright guys, in this section we're going to be discussing implicit differentiation and what it means to find the derivative implicitly. But first we need to discuss what implicit and explicit functions are. Okay, so as an example, if you remember a reciprocal function, 1 over x, this function that is very familiar to us can be implicitly defined as x times y equal to 1. We're already familiar with the explicit form, and that's if we solve for y, we have y equals 1 over x. And we know the graph of this function, and of course we can write it as x to the negative 1 so that we can differentiate, and that's what we've been doing. The reason we do that is so we can use power rule and bring the negative 1 to the front and differentiate this function explicitly. So, but what we're going to be discussing in this section is how to do the same thing, how to find the same derivative, dy dx, without having to solve for y, or without having the function explicitly, but instead we differentiate implicitly. In this case, xy equals 1. Now, remember the explicit form means that you have y as a function of x, or that your equation is solved for y. If this is not the case, then you have an implicit form, and we're going to see how to differentiate a function implicitly. Okay, so here are a couple of guidelines for implicit differentiation, and we have 4 simple steps. The first one is to differentiate both sides of the equation with respect of x. Remember here, guys, x is our independent variable, and y is always going to be a function of x for us. Okay, so always think of y as a function of x. Number 2 says collect all terms involving dy dx on the left side of the equation and move all the other terms to the right of the equation, right? So once we've differentiated both sides implicitly, we're going to have to use chain rule every time we differentiate a term that has y in it, the variable y. Because y is a function of x, then we're going to apply a chain rule, and we're going to get that dy dx every time we encounter a term like that. And then we're going to have number 3 is factor dy dx out on the left side of the equation, and then we'll solve for the dy dx on step 4. We'll finish that way. So let's look at an example here, and we'll go through the steps here, or the guidelines, to solve the following example. All right, so we have x squared plus y squared is equal to 9. We're going to differentiate with respect of x here. This is our first step. Notice how I'm not moving anything, or I'm not doing anything to the equation or solving for y. I'm going to differentiate this implicitly. So you differentiate on both sides, or the whole equation. So then we're going to take the derivative with respect of x squared plus the derivative with respect of x of y squared equal to the derivative with respect of x of 9. Okay, so here we're going to use our rules, our basic rules that we've been discussing in the previous sections. And we know the derivative of x squared is just 2x, right? And the derivative of the derivative of y squared is 2y. But since y we said is a function of x, you got to do chain rule, and derivative of y is just dy dx. And of course, derivative of a constant is just 0. Okay? And the next step is to go ahead and move everything else that doesn't have dy dx. Any terms that don't have dy dx, move it to the right side. Keep the dy dx on the left. And then we're going to factor. In this case, we don't have to factor anything because we only have one term. Well, we just solve for dy dx. And we have dy dx moving the 2y to the other side. We're going to have negative 2x divided by 2y. And then, of course, the 2's are going to cancel out. And we end up with our derivative, dy dx. So the derivative of y with respect of x is equal to negative x over y. Okay, here's another example. And we're going to do the same thing, follow our same guidelines. We'll take the whole equation, take the derivative respect of x, so the whole thing. And we're going to have, we're going to do term by term here. Derivative of x cubed minus the derivative of x times y plus the derivative of y squared, all of that equal to the derivative of 7. And remember, guys, I'm going to stop saying with respect of x, because everything is going to be with respect of the independent variable. And most of the time we use x, so whatever your independent variable is. And then we go ahead and use the rules here that we know. Power rule. We're going to have to use some product rule on this next one, because you have x times y. And remember, always think of y as a function of x. Okay, so then you really have two functions here, y times x, or x times y. So there are two functions of x, right? So then product rule will apply here. So we have derivative of the x is 1 times y plus x times derivative of the second one, which is y, and it's just dy dx. So that right there was just derivative of xy. And then we have the derivative of y squared would be 2y, power rule, and then chain rule, we do the dy dx. And of course that's equal to 0. Derivative of a constant is just 0. Now our next step is to just kind of group, simplify it a little bit, distribute the negative so that we get rid of that parenthesis and we can group all the terms that have dy dx. So if you follow here what I'm doing, all I've done is I've distributed the negative to get rid of the parentheses, and now I see clearly I have two terms that have dy dx. Okay, first I want to move everything that doesn't have dy dx to the other side, to the right side of the equation. So, and you can rearrange these terms any way you want as long as you keep their signs. So I'm putting the 2y dy dx first, minus y dy dx on the left. Okay, all I've done is I switched the order there, but that's okay. And then equal to everything else. I moved the 3x squared minus y to the right side, and I just wrote them in that order, y minus 3x squared. Okay. Now our next step is to factor. This is step 3 from our guidelines, to factor the dy dx, right? Notice how you have dy dx in common on the left. And then we're finally going to solve for dy dx by dividing both sides by 2y minus x. So once we do that, we'll get our derivative. Remember, the ultimate goal is to solve for dy dx because that is our derivative. All right, and there we have it. All right, so here we have another example. Sine of x plus 2 cosine of 2y, it's equal to 1. All right, so we're going to differentiate implicitly as we've been doing it. Notice how it would be really hard to solve for y for an equation like this. So this is where implicit differentiation comes in handy. Right? Take the derivative with respect of x of sine of x, and we'll do that for each term of the equation. All right, derivative of 2 cosine of 2y equal to the derivative of 1. All right, so derivative of sine is cosine plus you have the derivative of 2 cosine 2y. And we're going to have a little bit of chain ruling here, double chain rule, because remember y is a function of x. So we always have to think about that when we differentiate with respect to x. We have 2 sine of 2y, and then chain rule on the 2y will give us derivative of 2y is 2. So we're going to multiply this by 2, and then of course dy dx is the derivative of y here with respect to x. All of this is equal to 0, right? The derivative of 1 is just 0. And then we proceed to solve for dy dx. Okay, well, let me clean this up a little bit, this term. And we have 2 times 2 is 4, right? Sine of 2y times dy dx equal to 0. We'll move the cosine x to the other side. And then we're going to solve for dy dx, right? By dividing both sides by a -4 sine 2y. All right, so there we have it. Dy dx is equal to cosine of x over 4 sine of 2y. The negatives canceled out, guys. Okay, so here's another example. We're going to take the derivative again on both sides of the equation with respect of x. And we have the derivative of cosecant of x is going to be equal to the derivative of x times 1 plus tangent of y. So right away, notice how we have a product on the right side of the equation. So you can guess what we're going to use here, right? All right, so derivative of cosecant is equal to negative cosecant times cotangent. That's going to be equal to, product rule says, right, derivative of the first, which is x, the derivative of x is 1 times the second function, which is just 1 plus tangent x, tangent y, plus the first function, which is x, times the derivative of our second function, which is everything in that parenthesis. Derivative of tangent y is secant square y, and again, chain rule, right? Because y is a function of x, we'll have our dy dx as well. All right, so cleaning this up a little bit, we'll have on the right side, we just have a function of x, so our dy dx is actually on the right. But that's okay, we can switch sides here to solve for dy dx, either way we want to. So I'm just moving everything to one side, so instead of having it on the left, I'm going to keep our dy dx on the right for right now. I moved everything else to the left, and then finally I'm going to just switch. I'll swap the two sides here just because I'm used to having dy dx on the left, but it's the same thing. Finally going to take everything on the left, we moved it to the right, right? And then to solve for dy dx, we'll just divide by x times secant square of y. There we have it. Okay, here we have another example with a natural log and some algebraic expressions. We're going to take the derivative, as we've been doing it, on both sides of the equation. And some of these you can do in your head, so I'm going to go ahead and just do the derivatives, stop right in the d dx. You can apply chain rule, power rule, chain rule, and all the other basic rules from the previous sections that you should already know. So derivative of 4x cubed is equal to 12x squared plus the derivative of ln y squared of y squared is 1 over y squared is the derivative of ln, a natural log, times chain rule says derivative of y squared is 2y, and then of course dy dx, because y is a function of x, plus 2 dy dx equal to just 2. Derivative of 2x is 2. So cleaning this up a little bit, couple of things simplify. We end up with 12x squared plus 2 over y dy dx. Okay, plus 2 dy dx equal to 2. Now notice here I have two terms that have dy dx, and before I factor dy dx, I have to move everything else. Any term that doesn't have dy dx, move it to the right side in this case. So I'm going to move this 12x squared to the right, and then factor out the dy dx of the remaining terms of the left. So once I do that, I end up with dy dx times 2 over y plus 2, all that equal to 2 minus 12 x squared, right? Finally, we solve for dy dx, and we just divide both sides by 2 over y plus 2. Okay, I'm going to go ahead and simplify a little bit too here while I'm moving everything. And I factor out a 2 on the top, the numerator, and that's going to cancel out with the 2 on the bottom there that I factor out as well. Now, because I have a fraction on the bottom, I don't like to leave it as a fraction of fractions, so I'm going to put it together and just kind of condense it a little bit, so the solution or the derivative looks a little bit more presentable here. So again, just combining the denominator there, I get 1 plus y over y, and then rewriting it as just one fraction, I end up with this. The y ends up multiplying the 1 plus, and that should be a minus, guys, minus 6x squared divided by 1 plus y. It's a little typo there. Okay, another technique that we're going to use in this section is logarithmic differentiation, and on occasion it is going to be convenient to use logarithms to help us differentiate non-logarithmic functions. It's either going to make it easier, simpler, more efficient, and it will also help us find derivatives of functions that don't fit any of the basic rules that we've discussed so far. So first, let's kind of recall some basic rules that we've seen, so not to confuse this procedure with rules that we've already done. The first one is our simple and the easiest rule that we have here, constant rule, right? As we know, the derivative of a constant is going to be equal to 0. Okay, so if I have the derivative of an exponential expression in which the base and the exponent are constants, so in this case, my base is a, the exponent is n, and I'm pretending I'm letting a and n be constants here, so then a raised to the nth power would also be constant. And using our constant rule, the derivative of any constant is still 0. Okay? So notice how a is not the variable, it's not x, it's just a constant. And then n is constant as well. So then really a raised to the nth power is just constant itself. So taking the derivative of a constant would be 0, as we know. Here's an example. Derivative of, let's say, 2 raised to the third power. We already know 2 to the third power is 8. So here the point is that 2 to the third power is a constant itself. So the derivative of a constant is going to be just 0, right, using our constant rule. Okay. Our next example is going to come from the product rule. So let's recall what the product rule says. The derivative of a function of x raised to the nth power, right? And n is just a constant here, some real number. Remember, this is the generalized power rule, right? Using chain rule here, we have that power rule says, bring the exponent to the front, n times the function f of x raised to the n minus 1, so the exponent goes down by 1, times chain rule says to multiply by the derivative of the inside function, which is f of x. Okay, derivative of f there. Okay, an example would be, well, just a simple example here. Let's take the derivative of x cubed using chain rule. Sorry, not chain rule, power rule. That's going to be equal to 3x squared. Okay, so all of these examples we're already familiar with. I'm just recalling these because I don't want you to confuse these rules or these examples with logarithmic differentiation, and we'll see that. But our next example is the derivative of exponential functions, right? And we have a rule for that. So if we take the derivative of some exponential function, we have a rule that says that the derivative of a to the x is equal to the natural log of a times a to the x. Now changing x to f of x, and remember we've generalized all these rules with the chain rule. So instead of x, I'm just going to use f of x to generalize it, to have a more general formula. And we get that the derivative of a raised to some function of x is equal to the natural log of a times a raised to the f of x, this function, times the derivative of f. Now an example, easy example would be the derivative of 2 to the x. That's equal to the natural log of the base 2 times 2 to the x. Again, these are rules that we've already seen. We know what the derivative of a constant is. We know how to use power rule. We know how to use find the derivative of an exponential function. But now what if we get a function that looks like this, right? Y equals x raised to the x, where the base is a variable and the exponent is a variable as well. So to find the derivative of this function, you might be tempted to use power rule or even the exponential rule that we just saw in the previous examples, but none of those are going to apply here because both the base and the exponent are a function of x. So here's where we're going to use the logarithmic differentiation, and it's called logarithmic because we're going to use the properties of logs to solve for the derivative here. We're going to take the natural log on both sides with the purpose of using the power rule of logarithms to bring that power, in this case x, to the front here, right? And we have natural log of y is equal to x times the natural log of x. Because the whole problem was the base and the exponent were functions of x, but now I have them as a product using logarithms, and we can now take the derivative on both sides and go from there. So we have the derivative of natural log of y is equal to the derivative of x times the natural log of x. Derivative of a natural log is 1 over y, and then because y is a function of x, remember chain rule says we got to multiply by dy dx. This is equal to, we have a product on the right, we're going to use product rule, so derivative of x is 1 times the natural log of x plus x times the derivative of natural log of x is 1 over x. All right, moving the 1 over y to the other side, in solving for dy dx, we get that dy dx is equal to y times natural log of x plus, and then x over x is just 1. Now if we want to leave this expression in terms of x, we can always substitute what y was. If you remember what y is for us, is x raised to the x. So that was our original function, and we can just substitute that in here to leave everything in terms of x. All right, let's look at some examples here. I'm going to take the natural log against both sides. And notice how this function here is explicitly defined, and we could easily use product rule to find the derivative of this function, right? Because we have a product here, x times square root of x squared plus 1. But we're going to use logarithmic differentiation to see how it helps us find the same result in a different way, and maybe in even a more efficient way. So after taking the natural log on both sides, we're going to go ahead and use our rules of logarithms here to split this logarithm in the right. So if you recall, the product rule of logs says if you have a log of a product, you can split it into a sum of the log of the factors. And that's exactly what we're doing. And notice how I've also written the radical as an exponential expression with a fractional exponent, and so that I can use power rule and bring the 1/2 in this case to the front here in front of the natural log. Now after we expanded our logarithm on the right, we're ready to take the derivative with respect to x on both sides, and we're going to differentiate now this implicitly. We have the derivative of the natural log of y is 1 over y, chain rule, times dy dx equal to derivative of ln x is 1 over x, plus derivative of 1/2 natural log of x squared plus 1 is 1 over x squared plus 1, and remember we had the 1/2 in front, times the derivative of the inside function here, x squared plus 1, which is 2x. 2's cancel out, and we're going to go ahead and solve for dy dx by moving the 1 over y to the other side. So we have dy dx is equal to y times 1 over x plus 1, or sorry, x divided by x squared plus 1. Don't forget we had an x there. Now cleaning this up a little bit, we're going to just kind of condense or put those two fractions together, and we'll have the, find the least common denominator and just kind of put it all together in one fraction. And the denominator we have x times x squared plus 1, and on top we're going to end up with x squared plus 1 plus x squared. And then we can combine the x squares and we get the following expression here. Remember, we can always substitute the y for our function of x from the beginning, just so that we'll have everything in terms of x. And substituting y for x square root of x squared plus 1, we get this. Now after simplifying a couple of things, the x's cancel out, we end up with our final expression here for our derivative. Okay, here's another example where we can use logarithmic differentiation to find the derivative of this function. And we start by taking the natural log on both sides again. We get the natural log of y is equal to the natural log of that whole quotient there. Notice how we could have used the quotient rule to solve or to find the derivative of this function, but we're taking advantage of this technique or this procedure to make it go a little bit faster. Once we have taken the natural log from on both sides of the equation, we use our rules of logarithms or properties of logarithms to expand this logarithm on the right. Right? So we have a product on top, a quotient overall. We have some powers there, so we're going to use all three rules in here. We split the product of the numerator into a sum, and then the quotient split into a difference, and all those powers can be brought to the front of the logarithm using power rule. Okay, so notice how after doing that, we can take the derivative with respect to x of both sides of the equation. Very straightforward here. So we already know the rule for the derivative of a natural logarithm, and it's just we take the derivative of each term one at a time. So on the left side, of course, always 1 over y dy dx equal to 2 times the derivative ln x is 1 over x plus 3 halves times the derivative of ln x minus 1. It's 1 over x minus 1, so those go in the denominator. Same thing for the derivative of negative 1/2 ln of x plus 1. Okay, so the rest is just solving for dy dx, simplifying a little bit, making our expression look a little bit more condensed, more simplified. All right, so finding a least common denominator, we get 2x times x squared minus 1, and then on top we're going to get 4 times x squared minus 1 plus 3 times x plus 1 minus x times x minus 1. Now the rest is just expanding the numerator there and combining like terms and canceling anything that needs to be canceled and simplifying our overall expression here. So as you can see, we can combine some like terms and simplify our numerator. All right, so we end up with something that looks like this, and we're almost there. We can simplify a constant here. On top, notice how there's a 2 in common in the numerator there, so we can factor out a 2 and simplify with the 2 that is in the bottom in the denominator, and that's probably the last thing we can do. So we end up with this expression here. Okay, so here's one last example. This is a function that we can not do it with rules that we have. Product rule, quotient rule, chain rule, power rule, any rule that we've done so far. So we have to use logarithmic differentiation here. So we have a function raised to another function of x. So a function of x raised to another function of x. So we start by taking the natural log on both sides. And again, the purpose of that is so that we can bring that exponent, which is a function itself of x, to the front, right? So use power rule of logarithms to bring that ln x, as you see it there, to the front here. That's a coefficient there. So we do that. And notice how in the right I can rewrite natural log of x as natural log of x as natural log of x square, since I'm multiplying natural log itself of x times itself. Okay, and then now, I mean, either way would have worked. I could have used product rule, but since it's the same thing, I'm going to take advantage of that I know how to do chain rule to bring that 2 to the front, natural log of x, and then chain rule, derivative of the inside, which is 1 over x. Solving for dy dx, we get dy dx is equal to y times 2 over x, the natural log of x. And there we have it. Remember, you can always substitute the y for the expression in x, as we had in the beginning, if you want to have your final answer in terms of x.